Okay, so this example, for example, with Reisner Midland plate that we looked at many years ago. Okay, maybe I should say what it is. So this is sort of a elasticity model, but we have a very thin plate, such that what comes into the model is a thickness, which is called T here, of the plate. And so you get a problem, and you like to have finite elements and preconditioners that are uniform with respect to that parameter T. That sort of was the goal of the study. So this is, you can formulate this as a minimization problem, where you have a term that sort of blow up as T goes to 0. So you can see this is it's a minimization problem, so you can just write down what are the conditions in a continuous case for the system. You get a model where you have a parameter, and typically the standard tricks to sort of avoid this is to introduce a new variable, such that instead of having 2 phi and u as you have here, you get an extra one, and you get sort of a system like this, which is 3 equations in 3 unknowns. I don't want to go through all the details. It's more the kind of structure that is involved. So you see, as you look at this system, the operator typically depend on this small parameter. And even the problem will change form as, change type, excuse me, as t tends to 0. It will sort of naturally go from one type problem to another. So if we want to find a uniform preconditioner with this, what we have to identify is function spaces that will depend on t, but such that the norms of the operator going from its function space to the natural dual is independent of t. So that's exactly what you can do. And here is, just wanted to show you this such that it's natural how these spaces will just so come up. So for the 3 variables, 2 of them will naturally be in H1, while the last one will exactly be this kind of intersection space, such that in the dual you get sort of the natural sum space in. Okay, and just look at this space here. This is H minus 1 div, which is bigger than L2, intersected with L2. So for any t as a set, this looks like H minus 1. It looks like L2, excuse me, because it's going to be in both spaces. So it's naturally for every positive t in L2, but as t go to 0, it goes to the H minus 1 div norm. So you have typically this kind of effect to make this work. And at once you know seen what the function spaces is, which of course takes some time. You have to verify the Bredsky condition or something similar to see when it's well posed. But once this is done, you can at once write down the preconditioner. And typically you get a preconditioner here which reflects that where you have H1 as a space, you get something like Laplace inverse. And the other final operator you get here naturally depends on t. And if you look at this, this is a 2D problem in spirit, since it sort of is a plate model. If you look at this preconditioner down here, it's actually, it's like a 0-order operator as long as t is positive, which reflects that the function space here was L2. But when t goes to 0, it really goes to a differential operator here, because then as t goes to 0, this piece in the middle disappears, and it looks like it's really is a 2nd-order operator. So in this case, the preconditioner is a 2nd-order operator, not the inverse of a 2nd-order operator, reflecting this case that in the limit, this acts like an integral operator, like a smoothing operator in the 3rd component. So you can sort of read everything out of knowing the regularity of the problem. Okay, I think I need to speed up. So maybe I should, here's a control problem where there also is a small parameter. I think I just skip that since, and do instead what we refer to as in some contexts at least as the time-dependent Stokes problem. So this is motivated by you having the time-dependent Stokes problem, and you want to do time-stepping schemes for it. So if you want to do time-stepping schemes for it, you might end up with a system like this. So this is a sort of an interesting system, because when epsilon is large, it looks like Stokes' problem. When epsilon is small, it looks like the mixed formulation of the Poisson equation. And the point is then that you like to have preconditioners for this, which are independent of the time step, which then we reflect as epsilon square here. So now the recipe is of course clear. You just have to find what are the function spaces that make this thing well post independent of t. But you know, here is sort of even more interesting, because we have already seen that for t equals 0, this operator is well post in two different spaces, either h_div times L2 or L2 times h1. So this should sort of indicate there are two preconditioners around, and it is. So you can give two kind of spaces. Maybe we should just go directly to the preconditioner. Remember, for epsilon equal to 0, we have this I minus grad div inverse identity, and we also had the one which had identity here and the Laplace inverse down here. So if you look at the two we have here now, we both have the property that when epsilon is big, they basically look as a Stokes preconditioner. But as epsilon goes to 0, this will go to this h_div preconditioner, h_div here and identity here, while this one, as epsilon go to 0, will go to identity here and Laplace inverse here. So you can sort of read out two different structure, but you can show that they both are uniform, and they reflects two types of spaces where these operator having the parameter are well post. Okay, and actually many people have looked at this for the discrete problem, which I'm now going to do the last 10 minutes. And what you find in the literature that most people, or nearly all people, have used this one, but not this one is hardly mentioned in the literature, and I'm going to explain why in the end. Okay, so let's now go to discrete problems. All this was about continuous problems, but we all know that when we compute, we have to look at continuous problem, discrete problem, excuse me. So how does all this setup with precondition and the continuous problem, how does it relate to a discrete problem? Well, we will argue that if we now have identified the correct preconditioner for the continuous problem. So let's say we have done that. We have some problem, we've been through this process, we know the function spaces, we know how to precondition a continuous problem. Then of course we need to have a stable discretization. We're going to apply some finite element spaces. The method has to be stable, and we know that is an additional property. Then we will argue that we also know the structure of the discrete preconditioner. So this is sort of the program in some sense. So how do we do that? Well, instead of then using the Bretzi theory, let's use sort of the even more general babushka theory for bilinear forms, systems, and then finite elements. So we're having some kind of a bilinear form, and we're just going to look at the weak formulation of this type. We're not going to assume that this bilinear form A is anyway coercive, but for the simplicity here, let's assume that it's symmetric, such that we get symmetric problems. We're also going to assume that it's bounded in this function space X that we're looking at. It can be anything, such that we can say that the system is of the form AXF, where F is then in the natural dual space. Okay? This is sort of a Hilbert, let's say it's a Hilbert space setting. We have continuity and everything. Okay? Then what basically Babushka's theory says that if this bilinear form is bounded, satisfies the inf sup condition, then this equation has a unique solution, and the operator is bounded by the bounds on the bilinear form. The inverse operator, which goes then from x star to x, is bounded by the inverse of the inf sup constant. That sort of is this is really a little more general theory than the Bretzi theory, because now we have to look at the whole system at once.